Module 6 is where we're going to take what we just in Module 5 about the various components, the circulators, isolators, cavity filters, transmitter combiners, receive multicouplers. We're going to use some of those devices to try to solve some real world problems in interference. And I don't know how much you get involved in interference resolution. I think that's a big part of your job, is tracking down interference. So we're going to talk about some of the ways to identify interference, where it comes from, and how we can fix it. We're going to talk about 3 different types of interference: transmitter noise, receiver descents, intermodulation, and then we're going to discuss some possible techniques that can be done by the system owner to try to fix interference if it occurs. Nothing's 100%, everything helps. So let's define interference. What is it? It's defined as the presence of one or more unwanted signals appearing on your receiver that will reduce, degrade, or eliminate the reception of the desired signal. So you're trying to hear one thing and you're hearing something else instead. Interference can be self-generated as a result of the system receiving interference or as a result of external signals, either at the same site or a distant site. So part of our job as an interference hunter is to try to find the source and eliminate it or reduce it. So we need to know the enemy. What are the types of interference? First, we've got transmitter sideband noise. This is the noise that every transmitter makes. These are off-frequency emissions that can get into nearby receivers that we want to reduce. We have receiver desensitization. A receiver is meant to pick up fairly weak signals. That's what it's designed to do. If you hit it with a strong signal, you will actually make it less sensitive. It's kind of like if you're in a crowded room full of people and you're trying to listen to one person and 100 other people in the room are talking. You are not going to be as sensitive trying to hear the one person you do want to hear. So desensitization is also called desense. A longer name is dynamic range overload. You're basically overloading the receiver with too much signal. And a third type of interference most of us are familiar with, intermodulation. This is a type of interference that is generated either on site or away from site. The 2 types of intermod are active and passive. Active means it occurs in an active device, something that has an amplifier or electronic component to amplify the signal. Or it could be passive intermod, or PIM, meaning that it happens on some passive device that just provides a point where 2 or more signals can mix together and produce a third signal, which then interferes with our receiver. So intermod has a lot of different ways it can occur. You may hear terms like 2A minus B or A plus B minus C, and we'll explain what those mean, but those are different mechanisms of intermod. So whether it's transmitter noise, receiver descents, or intermod, they're all different symptoms of interference, and they have similar types of remedies. So sometimes you'll see transmitter noise and receiver descents lumped together and called TNRD, because after all, transmitter noise puts out high-level signals, which can then become receiver descents in the presence of a nearby receiver. So they're kind of different forms of the same thing, which is unwanted signals. So where can interference actually occur? Well, it can occur right on your receiver channel. If I'm at 151.5 and another transmitter is on 151.5, he is co-channel. There's no way I can put a filter on there or anything else to filter him out because he's on my receive frequency. So that's called channel interference. The other type is called adjacent channel. Well, he's not on my channel, but he's on the one right next to it. And that's still a problem because his transmitter noise curve is still high enough to get into my receiver. And beyond adjacent channel, there's alternate channels. That's the one not adjacent, but after adjacent, so the second channel away. So for instance, 25 kilohertz away rather than 12.5 kilohertz away. It's weaker than the adjacent channel, but it's still strong enough and close enough to be a problem. So we want to avoid adjacent channels and alternate channels. And we talked about how transmitter combiners have a minimum separation. That's to keep these adjacent and alternate channels away from those other transmitters. But interference to a receiver. So the magnitude of any interference is really a function of the signal strength, its distance from your receiver, and its separation in frequency. So the co-channel is the worst, really hard to get rid of. Adjacent channel is bad, alternate channel not as bad. Again, these can occur at the same site or a distant site. And it's very common that the source of your problems is sitting right next to you in another rack or even in the same rack as your receiver. So before you start looking outward, look around at your site to see what may be causing it. So what we're going to do is a little exercise to show how we can eliminate interference at a site. So we have a curve here, and what this exercise is going to try to do is try to find how much isolation is required to prevent a transmitter transmitting on 460 megahertz. How much isolation do we need to keep that from affecting 5 megahertz away at 465 megahertz? So the blue curve shows that we have a transmitter at 460 megahertz, and the blue curve is the spectrum analysis of that signal. Notice it's not just a perfect spike, it has a lot of sideband noise going on either side from that signal. So there's no such thing as a pure transmitter signal. Every transmitter puts out energy plus and minus from its center frequency. Our job is to try to reduce that energy at our receiver. So the red line is the FCC specification for power curve. The blue line below is the receiver sensitivity. So we're going to try to look at 465 and see how we can reduce the transmitter sideband noise energy as seen 5 megahertz away. And we can see that here we have a receiver which has a sensitivity of about minus 120 dBm. And at that received sensitivity level, our transmitter noise is still 76 dB above that. So we're getting too much noise into the receiver. How do we reduce it by 76 dB? So let's look at what we've got. Transmitter noise is what we're looking at here. It's the interference resulting from the excess signal generated by a transmitter, which is outside the bandwidth limits of the desired frequency. So in our example, we were at 460 megahertz, and we are experiencing transmitter noise 5 megahertz away at 465. So transmitters can emit radiation far away from their centers. Some transmitters are better than others, And that's just a function of the manufacturer and the quality of the transmitter. Well, how will we know if we have sideband noise? Well, if you're listening, you'll hear complaints of reduced coverage, and you will hear to the transmissions being cut off in mid-sentence, because every time a transmitter is keyed, it will walk on top of the receive frequency, and you'll hear people complain about that. So what are some simple things we can do about it? Well, here's the simplest thing you can do. If you're transmitting, say at 460, and your receiver's at 465, and you have two antennas that are close to each other, that's part of the problem right there. Because of the proximity of the two antennas, too much transmit energy is getting into the receiver. So what can you do quickly and easily? You can move the transmitter antenna away from the receiver antenna. Now, which one goes on top and which one goes on the bottom? It really doesn't matter as long as they're physically separated. And this is a inexpensive way to provide a lot of isolation without having to buy any new hardware. So another thing you can do, if that's not an option, is to add a notch on the transmitter. Tune that notch to the transmit frequency, and it will then attenuate the sideband noise on anything on the no you actually you tune it to the receiver frequency, so it will notch up, it will keep signals out, it will notch out signals on the receive frequency. Okay, so you put a notch filter in the transmit line, tune it to the receive frequency, and notch out the signals on the receive frequency. So let's look at an example. Here is a receive sensitivity line of about minus 115 dBm. And we just added a notch filter to it. Without getting specific numbers on here, you can see that the notch filter tuned to the receive frequency does a great deal for cutting back on the sideband noise frequency 5 megahertz away. So that's one thing we can do. Another possibility is to add a band pass filter with the filter tuned to the transmit frequency. So now we're allowing just the transmit frequency to pass through to the transmit antenna, and it attenuates things at the receive frequency. So just the opposite of what we did with the notch filter. And let's see what effect that has on our receiver. Well, now we see we put that bandpass filter on. We've lowered the transmitter noise curve below the receive sensitivity line at the receive frequency. So that's certainly a good thing. So either one of those will help us. So that was transmitter noise. Let's talk about effect, which is receive desensitization. Again, this is a decrease in sensitivity. When somebody yells at you all day, you become desensitized, and that's what's happening. One or more strong signals at or near the desired receive frequency, also known as dynamic range overload. You can filter it out if it's near the receive frequency, but if it's right on the receive frequency, you can't filter it out, so you have to go to the source and either eliminate the source or isolate yourself from the source. So let's look at, here is a receiver selectivity curve. This indicates the range of frequencies that the receiver will respond to. Now, and by way of convention, blue line means receive and red line means transmit. So our blue receive curve, now we have a nearby transmitter which is transmitting and falling within my receive curve. So that's a problem. And how will you know? Well, these symptoms look like the same thing as the symptom for transmitter noise. And that's because they're really two different sides of the same coin. Complaints of reduced coverage, complaints of transmission being cut off, and they'll be off and on as the transmitter is keyed and unkeyed, which makes it hard to pin these down. If interference comes from a broadcast transmitter, you can listen to it, it's continuous, and you can ID who it is. And that's great if it's a high-powered broadcast transmitter, but oftentimes it's going to be some intermittent transmitter that you have to be lucky enough to hear it when it happens. So you may have to place some equipment on site and walk away and let the equipment listen for it to happen. It may only happen once or twice in a 24-hour period, but just enough that the user gets annoyed by it. So it takes patience to track down interference, and we're all patient people. So, what do we do about it? Kind of the same things we did about transmitter noise, because again, it's two sides of the same coin, so the remedies will be similar. What can we do? Once again, we can separate the transmitter antenna from the antenna. And I don't care which one is which, as long as they're separate from each other. Now, you remember on the transmitter noise issue, we were putting filters on the transmitter side. Now, since we own the receiver and we're getting receive descents, we can do something on our receiver. So once we identify what the problem is, we can put a notch filter on the transmitter's frequency. Again, if it's on the same channel, this filter won't do any good, but if it's an adjacent channel or a co-channel or something nearby, we can put a notch filter to notch out that offending transmitter frequency. Again, here's our blue line for our receiver curve. There's our selectivity curve. Here's our unwanted transmitter nearby. And when I say nearby, I mean nearby frequency, not necessarily nearby in space. We put a notch filter in on the right on top of the transmitter frequency, and we were able to cut it down from interfering with our receive sensitivity. And just like before, where we had both a notch and a pass filter solution, the bandpass filter solution is to put a bandpass filter on our receiver to increase the selectivity. Here's our receive curve again, our unwanted transmitter energy, and now we put a bandpass filter on and a notch filter, and it cut all that stuff out while keeping our selectivity curve intact. So that was transmitter noise and receiver distance. Two different effects, but really the same cause and some of the same solutions. So now we're going to talk about intermodulation or intermod. An intermod is a type of interference that has to be generated either locally or it's the presence of an undesired signal on our receiver frequency as a result of two or more signals mixing together, resulting in a generated signal that is on or near the desired receive frequency. So we have to generate that signal. It doesn't occur naturally. So we have to have two or more transmitters which are on the air at the same time and have some place to mix together. And by mixing together in the right proportion, we'll generate a signal on our receive frequency. These interfering signals might be fundamentals or harmonics. So when two or more signals mix together, not only do the original signals come out, but we get harmonics and we get sums and differences. Sum is the mathematical sum of the two frequencies, and difference is the mathematical difference between two frequencies. And we can get those different counts of sums and differences, and as unlikely as that seems, it happens all the time. When you have a crowded site, you have all the possibilities for intermod to occur. And they could be active, occurring in an active device, or they could be passive, occurring at a passive place. So what are the different mechanisms? You might see the terms third order or fifth order or seventh order intermod. What does that mean? What that means is it's describing the mechanism that of the signals that are combining to produce your undesired signal. So the first type we'll talk about is where we have two signals mixed together, an A and a B, and they mix together to produce a third signal, which is on a receive frequency that we want. So this can occur actually out of band. For example, if you have 150 megahertz signal and 151 megahertz signal, and they'll combine to produce a 301 megahertz signal, which could be a receive frequency. Now, 300 megahertz is a military aviation frequency, but still, that combination can occur. You could have a very common type of intermod called 2A minus B, where you have the second harmonic of the first transmitter and the fundamental frequency of the second transmitter. The first one subtracts from the second to produce another signal in band. And we'll give examples to these on the next slide. So that's a 2A minus B combination. Then you might have a three transmitter combination. It requires three transmitters to be up and transmitting at the same time, which becomes all the less likely to occur, but it could happen. So you have an A plus a B minus a C. So and because of that combination, it will occur in the original frequency band, causing you a problem. A fifth order combination that is very common is a 3A minus 2B combination. And when you do the math, 3 times a third, the third harmonics mixed with a second harmonic will produce something in the fundamental band you started with. So that's why, even though it looks exotic, it can happen pretty frequently. So let's do some examples. A second order combination, and the reason they're called order is if you look at the coefficients of the variables there, they're ones or twos. So you add the coefficients together to get the order. So second order, you have like 1A plus 1B. That's why it's called second order. An example would be 150 megahertz plus 151 is 301 megahertz. That's a second order. The reason that doesn't seem to be a problem is typically it will give us combinations that are outside our frequency band and don't bother us. They might bother somebody else, but they won't bother us. Then we have a third order combination of A plus B plus C. And this is an example where, for example, 3 VHF frequencies can combine together and give us an interfering signal in a totally different band. So we got 3 VHFs, 150 plus 149 plus 151, add them together and you get 450. And 450 is a land mobile radio band. So we can have 3 VHF signals that produce intermod in the UHF band. It can happen, and it has happened. So an in-band type of intermod that we can see often would be an A plus B minus C combination. And here's an example where signals in two different bands combine together in the right combination. So we have 450, 150 is 600 minus 149 equals 451. So now we have a UHF and two VHF frequencies create an interfering signal in the UHF band. So that's a problem. So then we have a fifth order combination called 3A minus 2B. An example of that is the third harmonic of 152 megahertz minus the second harmonic of 151 megahertz equals 154 megahertz, which could be an interfering signal. It doesn't have to be right exactly. The math doesn't have to work out exact. If it's close enough to be an alternate or adjacent channel, then it could be an issue. So you can see there's all kinds of combinations. Well, how do we figure out all these combinations? Do we have to sit and do all the math for all this? Well, fortunately, there is software out there that will predict this, but software is only as good as the information you give it. So if you have an intermod prediction program, you can have uh, a it wants to know all the frequencies all the transmit frequencies that are on the site. It wants to know what the receive frequency you're dealing with. And so the lost my the combinations can occur in any different way, and when you use the software, you have to know what your frequencies are that are present either on site, or if you know about signals that are off site, then they can be a problem. And somebody was asking about the bandwidth of a harmonic product. So yes, the bandwidth does increase with the harmonic. So that's something that the software will keep in mind as well, because it doesn't maintain the tight limits that it typically has when it's first generated. So you have to keep all that in mind. That the software knows how to do that, but you have to know what the original transmit frequencies are. So some of the basics of intermod, you need to know that intermod is a function of the strength of the interfering signals, the bandwidth, and the sensitivity of the receiver. So bandwidth is important. You need to know how wide is the window the receiver is going to have to deal with, and what's the bandwidth of the signals coming in at it. Now, the active intermod combinations that occur at an active device will be stronger because the signals coming in can actually be amplified inadvertently by your own devices on site. The order of the intermod mix, you can get even order combinations or odd order combinations, but the odd order combinations are generally the only ones you care about, because when you do the math, they will be the ones that result in interference in the same band as your receiver. And also, since the fundamentals are going to be stronger than the harmonics, your lower order intermod combinations are going to be stronger than your higher order combinations. So a third order intermod product is more likely to be a problem than a fifth or seventh, ninth order intermod, just because of the strength of the signals involved. As the harmonics get higher, the signal gets weaker. So where can this intermod occur? It can occur If it's an active intermod, it can occur in transmitters. It can occur in receivers. Multicouplers, that's a common place where intermod occurs because that's where all the receivers come together. So, and there's active devices in there. So that's a common place where intermod can occur. Passive intermod, you may hear the term PIM and PIM rated devices. So intermod can actually occur where there's no amplification. It can occur in connectors. It can occur in your antenna, in your transmitter combiner, which is a passive device, or even external devices. It's been known to occur on fence posts, on bad grounds, on tower junctions, on welds where dissimilar metals are present. The only good news about intermod is in many cases it is predictable. If you know what the frequencies are, if you monitor what's going on at the site and put them into your software, it can predict what some of the possible combinations can occur and help you track it down. And it'll do the math for you and say, these are the possible third order hits, and these are the possible fifth order hits. So there is some help available. So again, when you're playing detective and trying to track it down and the users complain that other users are suddenly appearing on your frequency, well, if you can actually hear them in an analog system, that's great. In a digital system, you may not hear them, but it will cause audio to drop in and out as the interference occurs. And again, you can identify it through the software and try to identify which will then get your fundamentals and harmonics and determine the possible combinations. So if we're getting intermod, once again, we're going back to what can we do to resolve some of the issues. We look at transmitter B are combining to cause intermod on receiver A. We can add bandpass cavities to the receiver, again, assuming it doesn't occur right on top of the receive frequency. If it's nearby, we can filter it out with bandpass cavities. And once again, we can isolate transmit antennas from receive antennas so that we don't have a huge amount of transmitter noise that will produce intermod close to the receiver. Keep those signals isolated. We talked about how we can put isolators on the transmitter and bandpass cavities. So we can try to fix the problem at the transmitter side by putting isolators and cavities on the transmitters. Now, some of the good transmitters have some of these isolators already built in. We can always, there's no harm in putting a bandpass cavity on the transmit frequency to try to cut down on intermod. So if you're causing it, then you should be the one fixing it. What about external intermod? If it's not occurring on the site and we don't really know where it's coming from, the best we can do, keep the radio site clean. And by this we mean identify any places where intermod can occur, where a mixing point might be present. And we can identify and remove any dissimilar metal joints, like galvanizing where you have zinc on steel, or if you have connectors where you have nickel on brass, that kind of thing. We want to make sure we don't have a lot of dissimilar metal junctions where mixing can occur. Any metal parts, we want to ground and bond them so any unwanted signals will pass to ground. Let's see. Okay, I got about 10 more minutes until next break, I guess. Uh, Isolation. Remember, we wanted to get 76 dB of isolation. So we can consider a couple different ways to get there. Just the fact that there's insertion loss of components, well, that insertion loss will by itself knock down the transmitter noise curve. But again, that's not the total solution. We have to consider filtering, we have to consider antenna isolation, and we have to consider the characteristics of the transmitter and receiver that we're using. So insertion loss between filters and transmission lines, we could gain anywhere from 5 to 10 dB of isolation. But again, who wants a lot of insertion loss? We can filter either bandpass or notch filters to give us anywhere from 25 to 70 dB of isolation, depending on where the signal is and what the selectivity of our filter is. And to review our section on filters, here again is the characteristic curve of a good sharp bandpass filter, and it passes the frequency that we want and it attenuates everything else. So here's back to our original problem where we had 76 dB of isolation that we needed, and overlaid on the blue curve is the yellow curve, which is a bandpass filter curve, and it gave us 30 dB of isolation, 5 megahertz from the transmitter. So at 5 megahertz, it knocked it down 30 dB, which is great, but it's not the whole solution. And we had notch filtering where we had a different configuration to use a filter that notched out the frequency that we don't want passing through. So here we applied a notch filter to our curve, and in this instance it gave us 50 dB of notch, which is really good, but we're still 20 dB short of the goal. So again, it's getting in the right direction, but we're not quite there. What about this antenna isolation we've been talking about? Well, that is a really good way to do it without additional hardware. Vertical isolation, meaning separating the antennas vertically, is the best way to do them. These high gain antennas that we use have very little direction above and below the antenna, have very little energy radiated above and below the antenna. So by vertically separating them, we can get a lot of isolation, anywhere from 25 to 55 dB in the vertical direction. Here's a curve which is not to be relied on, but just gives you an idea what will vertical isolation do for us. And so we got different colors for each frequency band. So let's look at the VHF band in the green. And if we were to, this tells us that if we separated two VHF antennas by 10 meters, we would get about 56 dB of isolation, which is pretty good considering all we did was move this antenna 10 meters vertically away from the receive antenna. And you'll get more isolation at the for shorter distance the higher you go in frequency, because it's a function of wavelength. Wait a minute. Okay. What about horizontal spacing? Well, sometimes we're not on a tower and we don't have the option to separate antennas vertically. In that case, we want to look at horizontal antenna spacing. And this is good, but it's not as good as vertical. Because the antennas radiate in the horizontal plane, it's going to take a lot more separation to get the kind of isolation we want. So here, the spacing may give us results that are anywhere from 15 to 45 dB. And so here's a chart again that shows us what's the effect of horizontal isolation. And picking on VHF again, if we are able to, if we want that same 56 dB of isolation that we had vertically at 10 meters, we need about 100 meters of horizontal space to do the same thing. So you can see that vertical isolation, if you can do it, is much more effective than horizontal isolation. So if you recall, our original problem was we had a transmitter at 460, a receiver at 465. The transmitter noise curve was 76 dB above our receiver sensitivity at 5 megahertz away. And we needed to get that isolation. And we looked at all these different things. So let's start looking at them together. So first of all, let's look at the insertion loss. So that knocked everything down 5 dB by way of across the board attenuation. So now we are only 71 dB above our sensitivity curve. The notch filter provided us 56 dB of isolation, which still left us 20 dB short. The vertical antenna isolation in our example gave us 20 dB, which still leaves us 56 dB short. But if we combine all those things together, we combine our insertion loss, our filter selectivity, and our antenna isolation. Now we've got 81 dB of isolation, and we're below our sensitivity, and we solved our problem. Any questions on what we did there? Okay. And a couple more slides and we'll wrap this up. Control station combiner isolation. When we have a control station, we're going to want isolation on that as well. So
hey,
we
Bruce,
can, yeah.
a question came up from Nikki. Why is minus 76 our goal? She wanted to refresh her where that came from.
Okay. Well, going back to the original problem, the blue curve there, and this is a sample. This is not a fixed figure in the real world, but this is a example we created, which uses typical numbers in the real world. Your numbers may vary, but we had the blue curve says that we have a transmitter at 460, and if we look at the emission of the transmitter, and we look at it 5 megahertz away at 465, and we look at where our signal level is there, our receiver at 465 wants a signal that is 120 megahertz below 120 minus 120 dBm is our receiver sensitivity. That's what we want to get. Anything above that is going to be we're going to hear the noise, and we don't want to hear the noise.
Nikki says she got it now. She understands, so you can move on. And Nikki's question: the neg 120, Nikki, that's a typical receiver noise floor. You get into the noise temperature. She asked a question, so I'm just trying to help move along.
Okay.
It's a temperature noise temperature of the system. So if you look at minus 20, that's kind of a good basement. I think we're good, Bruce. Thank you.
Okay, thanks. All right. Control station combiners, we want to make isolation on them as well. There is some inherent isolation in the combiner itself, but we can provide external isolation on that. It's easier if we have the type of control station combiner with separate transmit and receive ports on it, so we can filter it. Some people will put a D on there. That's not typically recommended because, you know, duplexers are designed for one thing. They're not meant to go with control station combiners. A rule of thumb they use in the design of these systems is they call it a 45-65 design rule. When we're putting these systems together for trunk systems and multi-carrier systems, we try to keep about 45 dB of transmit filtering by way of bandpass filters and such. On the receive side, we try to filter out the transmit frequency on the order of about 65 dB. And then for the antennas, we try to separate them enough in either horizontal or vertical space to achieve at least 45 dB isolation. So that's just a rule of thumb that is used. Everything's not hard and fast, but those are the kind of numbers we for typically. So some of the design rules that we use: try to keep the signal into the infrastructure receiver below neg 35 dBm. This is a rule of thumb. Anything higher than that is typically going to desensitize the receiver, and so it will increase the possibility of intermod and cut down on the sensitivity. So we want to keep our receive signals below that. Now, you know, intuitively you might think the stronger the signal into the receiver, the better, but that's not really true. There is a window between the receive sensitivity floor and the highest level that we want to maintain. And it's a fairly wide window between about minus 35 to minus 120. If you can keep your receive signal in that window, you're good. Some of these we already talked about. Keep receive signals below minus 35. Try to avoid any third order intermod products. Those are the ones that will be your biggest problem, because being third order, they will have signals happening. The reserve gain, that's talking about the reserve multicouplers. So don't run your receiver multicouplers too hot. The temptation is to run full gain, but you don't want maximum gain. For the maximum selectivity, so you can filter with smaller bandwidth filters, high Q filters, or in some cases crystal filters, which have a very high Q and good selectivity. You only use those as a last resort because they're expensive. Always designed for passive intermod in the network. Assume it's there. Use PIM-rated components. And try to minimize the number of channels in a single transmit network. The more transmitters you try to jam into a single end, the more potential problems you could introduce. So typically, transmitter combiners, 5 to 8 is probably the maximum number that we like to see.